So hello everyone, my name is Ajit Singh and today we are going to do this session number 5 on FloEFD, which is based on conjugate heat transfer. So let's get started. So the objective is to check the air velocity and thermal distribution inside the electronic enclosure, which is like CHT, which is conjugate heat transfer analysis, and it is inside a defined volume, or we can say the internal analysis. So let's move on with the hands-on. So this is the setup which we have in front of us. So let's create a project. This is the FloEFD ribbon bar, and you can click on wizard to start the project. So I want to start it with the name called inlet flow, INLET FLOW. Yes, let's click on next. Let's take the temperature in degrees Celsius or Fahrenheit. I think Fahrenheit would be better because I have all the inputs or most of the inputs in Fahrenheit. And this is the internal analysis, as I already told you. And the heat conduction in solids is an important factor here because it gives you the access to both you can say conduction and convection in the analysis, so that will be useful here. We can go to next. If you want to add radiation, you can click on radiation also. Okay, let's click on gases. Like we have to put air as a project fluid and default fluid also, and our default material is stainless steel 302. Here the default outer wall thermal conduction is this heat transfer coefficient, and that is 20. Okay, and let's move on to the next. Yep, I think this much is enough for the setup, and let's move on to other inputs. So here we have to apply the material to the important components. So the first of all, we have to apply the temperature to this heat sink, and that you can say the material to the heat sink, and that is aluminum. Okay, so we can go to the metal here and we can select aluminum. Okay, and let's move on to apply the material to the other components, and that is we can select one by one, or we can use this option call. Let's click on this and let me show you. Select all identical parts. When you click on this, it will select automatically all the identical parts, so you don't need to multiple select again and again. And let's move on to the other option by defining the material, and here we have to apply. Okay, so we have already created a user defined material, and in this user defined material I have to apply total component package. So this is a one-time job to create a user defined material, and it will be available for on on network as well as to the user. So it will be always increasing in the manner, and it will give you the idea that in which project you have made. So it will be mentioned in the subfolder name. Okay, so that you can judge it whether this material is correct or not for your utilization. Okay, now let's apply the PCB. Even the PCB is already made in user defined folder, so I can choose that, or you can use the PCB which is defined in the predefined if it matches the circumstances or in the requirement. Okay, so you can click on this and it's done. Okay, so now let's apply the insulator to the lids, because I don't want to see temperature interaction, or you can say thermal interaction or fluid flow interaction because of these. So I can make it insulator. I insulator, these body, these and these. Okay, done. Now we have to apply fan. So this face will be serving as an external inlet fan, so that means it will push the air from outside to inside. Okay, and we are going to use this fan curve Pabst DC and series 412. Okay, done. We can derate the fans to match the actual fan performance, but that is not needed right now. Okay, let's move on to the next. Let's move on to the application of boundary condition, and these faces is open to environment, so we can apply the environmental boundary condition with the environmental pressure rating, and you can click on OK. Okay, now that's it. Now let's apply the material, material heat sources. So this is creating 5 watt heat. Okay, now let's apply the heat source to the other component like this. So we just have to click on this component, and this is creating the heat of 4 watt. Okay, let's apply the temperature. So on all the 3 faces it is going to apply 100 Fahrenheit. Okay, so let's apply 120 Fahrenheit on this power source or power supply box. So this is 120 Fahrenheit to the power supply. So nearly everything is done. We are going to create some goals to match and get the accurate result on those specific targets. Let's apply the goal. I want to make a solver to work on the pressure, that is static pressure, average static pressure. Okay, to correct and give accurate reading of static pressure on a global domain. Then average temperature, which is here average total temperature of fluid, or you can say average temperature. Yep, you can click on and it will create these two. Then we are going to apply a surface goal at inlet of the fan. So we are going to apply surface goal, and we have to use the pre-selection. So we don't need to do this selection and again to the complicated areas. We just have to use the selection made in our earlier choices. So that is one of the easiest thing to do, and we are going to apply total pressure, that is average static pressure. Okay, then we can apply we can apply the mass flow rate. We can find out the mass flow rate on these faces. So we can click on this. It will be like this. Yep, and we can apply small chip maximum temperature and other selection. We can select these small chips and we can find out total temperature. Okay, oh, I think I made it a wrong selection. No problem.